roughly divided. I'm not saying exactly, but it is roughly divided into three portions. Okay, one is the implicit parameters, then the actual parameters, and then we are having the other variables, aggregates, and temporary. So let us see that what each of these things are, which we can store in the static storage allocation. Okay. So first and foremost, we are having a look at what an implicit parameter is. Okay. So now it is understood that it is primarily used for the communication with the calling module. Right. Typically, such a parameter is the return address to the calling procedure or return value of a functional procedure when it is not convenient to return this value in a register. So if the value is returned by a register, then we don't have implicit parameters. But if we are having something which is being returned from a procedure, okay, whether it is an address or it is a value, okay, at that time those parameters are called the implicit parameters, right? So we can understand that it is used for communication with the calling module. So when a function is called, procedure is called, okay, at that time this parameter plays a role. Now we are looking at the actual parameters. Okay, so now what are actual parameters? They contain the value or the address of the argument that is designated in a call to a module. So the arguments that we pass, the parameters that we pass, okay, those will become our actual parameters. Okay, so after implicit parameters in our static storage allocation, okay, we store all the actual parameters, and then we have another section wherein all the other variables, okay, that by this we mean the local variables, okay, the aggregate means the arrays and other records, okay, and the temporaries which are generated by the compiler, okay, the temporary variables, they will all get stored just in this particular section. Okay, fine. So we have in total three things which we can store in a static storage allocation strategy. Apart from these, okay, we have a few more things, okay, but those things we are not able to store in the static storage allocation strategy, right? So for that we have a next type, okay, which we will call as dynamic storage allocation. Okay, so before we move ahead to that, okay, now let's see that what happens to a procedure call or how a procedure call is managed with static storage allocation strategy. Okay, so first and foremost, in this slide, I have simplified the call to a procedure into three steps. First and foremost, what happens is we bring forward the values or we evaluate the addresses of the actual parameters, that is the arguments from the calling procedure, and store them in a list in the calling procedures data area. Okay, so in the data area, as we have already discussed, that we are having three things, right? Implicit parameters, actual parameters, and the rest of the things. Okay, so the actual parameters will get stored, right? Then what we will do is we will place this address of the parameter list in a register, and then we will branch to the procedure. So what we are doing, that once we branch to the procedure, the starting address or the base address of this list is stored in the register from which we can fetch, and this is how these variables can be accessed. Okay, which are our actual parameters. Okay, so prior to the execution of the procedure, both the implicit and the explicit parameters must be moved to the special locations that have been previously reserved in the data area. This is static storage allocation. So the data area will have reserved spaces for all these different parameters. Now, when returning to the calling procedure, the implicit parameters are loaded into the registers and a jump back to the calling procedure occurs as dictated by the return address. So where it has to return and what it is supposed to do, okay, that information you will get from the address that is stored in the register. Following this, okay, so this is how it functions whenever we are using static storage allocation strategy to call a stored procedure. Okay, when we are calling a when we are calling a procedure, okay, this is how it behaves. Fine. Now we are just taking our overview of when this strategy will be useful to us. Okay, so though the memory size allocated for the data is static, okay, we can change the content without increasing the memory space allocated to it. So we are not allowed to change the size, but we are allowed, definitely allowed to change the content. Okay, naturally, because we are talking about variables, we are talking about parameters, so the values will change. Okay, the global variables are declared ahead of time, just like the fixed array. Okay, so if we are having a fixed size array, then all the global variables will be declared likewise. Okay, now the lifetime of static allocation is throughout your program, right? So once the static allocation is done, so till the program execution is over, okay, every variable will be accessible. Okay, whatever we have stored in our data area, that remains accessible. Also, its position is known to us. Okay, with respect to the base address, we will know its offset as well. Okay, because it is all predetermined at compile time, right? So runtime, any variable can be accessed very easily. And that is why it has got efficient execution, because every time it doesn't have to calculate. All the values are known, okay, all the offsets are also known, right? So it is very efficient, okay, to access the values, and that is why it has got a very efficient execution. The only two drawbacks we have for this system is that if more space is declared, then we are going to waste the space. If we are declaring less space, then because we are not allowed to expand or rather change, okay, so at runtime some data may not be accommodated because of less space which is declared previously. Okay, so these are only the two drawbacks. Okay, but they are quite important when we are talking about nested procedures, stored procedures, okay, and dynamically allocated memory. Okay, in that cases this type of allocation is not suitable. Okay, so this allocation is used for the global variables in C, ADA, and Algol. Okay, it is also used for the constants that we declare in C language. Okay, only for Fortran 4, okay, all the variables are declared using this particular storage allocation. Okay, and whatever code in our language that does not require dynamic compilation, okay, that uses the static allocation. Okay, so here we are not having any concept of heap or stack allocation, okay, and everything is done at compile time. This is how static storage allocation functions. Okay, as such, it is very simple, but we need to get all the details of how it functions, because when we are designing our compiler, or we are when we are constructing a compiler, okay, all these things will matter, right? So what type of storage is required for what type of data, okay, that we should know. Okay, so this with this we are ending the static storage allocation strategy. I'm sure that everybody has got this, okay, very clearly. Fine. Now we are moving ahead to the next, okay, and which is used by all the modern languages like C, C++, Java, Fortran, version 8, 9, okay. Here we are very frequently taking examples of Fortran and Pascal, okay, because they are given in your book. Otherwise, you can always relate to the languages which you are learning, okay, or which you have learned so far, okay. In all these languages, right, this dynamic data storage is very useful. Okay, so what it does, it allocates space for global variables at compile time, and the space for variables of the procedures is allocated at runtime, right? Because global variables are already declared, right? And we know that how much space is to be allocated for them, right? So at for those we can decide it at compile time and do its allocation at compile time. Now, as compared to static allocation, the variable access is slow. The reason is we are going to access the addresses using a stack pointer or a heap pointer, right? But we have an advantage that when we are going for dynamic storage allocation, okay, at that time recursion can be implemented, right? We can also go for nested procedures also. We will see an example today wherein how dynamic data storage allocation strategy can be applied for nested procedures. Okay, fine. Moving ahead. Now here you can see that we are having in total three procedures, main, R and Q, and the sequence, or rather we can say the calling sequence goes like this. From main we are calling R, from R Q is called, Q is again calling R, okay, and then there is a trace back to main. So this is how we are defining our calling sequence. Now how these things are maintained, they are maintained in form of a stack of activation records. Okay, we will see what an activation record contains, but as of now let us simply understand that it is the data area for the various activations of functions or procedures. So once a function or a procedure is called, okay, an activation of the same is created and a stack of it is maintained. Following this? Okay, the variable space for the second instance and the first instance is different. Okay, so over here we can see that we are making two calls to the procedure R. Okay, one is called from main and one is called from queue. But when we are looking at the sequence, at the same time the first instance and second instance of R is alive, right? So here we are not going to override the content. This is not static allocation. This is dynamic allocation, right? So here you can understand that the data of the variables, okay, for the first instance and the second instance, both can be maintained and we can do some useful work, okay, with both these instances, correct? Okay, so let's try to understand this in detail. Okay, now when this allocation will be done, when a call to a procedure is made, at that time this allocation will be done. Okay, and allocation will be done in the form of activation record, right? So to begin with the allocation, okay, what happens is for only global variables and main is made, right? Then when main calls R, the data space for R is created. Then when it calls Q, the space for Q gets created. And then when there is another recursive call to R, another space for R gets created. Right. So here it is very clear that for each instance we have separate space allocated, okay, for the same procedure R. Okay. Now, when the procedure terminates, then what happens? When R terminates, the space for R will be released. Okay. So now this is the second call of R we are talking about. Then when it returns means the control goes to Q. Okay. Now when Q returns, this space, okay, marked in green, okay, this is just symbolic, okay, that will get released. Then the first instance of R, which is denoted by orange, okay, that space will get released. And when finally the main program will terminate, entire space, okay, that the runtime system was using will get released, right? Following this, so with the invocation, with the call to the procedure, okay, space is allocated, and with the termination of the procedure, the space is released, okay, in the same order, okay. So now let us try to understand that how our activation record structure looks like, okay. Now what your activation record contains, it contains return address, it contains static and dynamic links, okay, how they are useful in our dynamically allocated data area, that we will see, okay. Then it contains the address of the function result, right? Then the actual parameters, local variables, the temporaries, the compiler generated temporaries, then the machine saved machine status, and then space for local arrays. Now these positions, okay, that are shown in this diagram are only notional, meaning for different implementation the ordering of all these fields may be different. For example, the function result could be after the local variables. Okay, so if immediately after the static and dynamic links, we may have the actual parameters and the local variables and the function result. Okay, that may be possible. Okay, and it is also possible that here we have put the local arrays. Okay, they may be combined with the local variables, or it can be combined with the actual parameters. That may also be possible. So it is depending on the implementation. What it focuses on is we try to keep those things at the end, which may get expanded. Okay, so if some more memory is to be allocated, then it has enough space to expand. So that is why arrays and such things, okay, such records are kept at the end. But it totally depends on the implementation of the compiler, okay, how it is being implemented, that how the activation record structure is maintained. Okay. And here the third point in the slide, okay, that should be understood, that it is possible to change the location of these fields without affecting either the efficiency or the speed of the program itself, right? So the position of these fields don't matter. It totally is on the implementation of the compiler that where we are placing them. Okay, are you following this? Now let us try to look at what each of these things is going to contain. Okay, you may be asked to explain the activation record structure. Okay, then you must know exactly what is stored in each of these fields. So the return address is required by the program to return to the caller, right? So if a procedure is called, it may be called from another procedure, right? Say suppose P procedure is called from main, right? Then the return address will be required by our procedure P to return to the caller, right? So who has called it, it has to store its return address, right? Then we require static and dynamic links to access the global variables from our current procedure. Okay, so say suppose we are having nesting of procedures, okay, at that time it becomes very significant that we should have access to the variables which are accessible in that scope. So at that time, this static and dynamic link will play a very important role. Okay, that we will see with an example. As I told you, we will see an example of nested procedure. So at that time, we will be using this static and dynamic link. Okay, they are also known as access link and control link. Okay, now the address of the function result, right? So if there is a result or if there is a return value from a function, okay, then it is the address of the variable which is containing the result of the function. Now this address will be passed as an implicit parameter as we have seen previously. Okay, we are now very clear of what we are calling implicit parameters, okay, and what we are calling as actual parameters. Okay, so now next is the actual parameters. Then we know that there are local variables. Okay. So this pattern of putting the parameters one below the other, okay, it is quite similar to the one that we saw in static storage allocation, okay, in the beginning of the lecture. Then the parameters which are not arrays, okay, we will know that how much space is to be allocated for them, right, depending on its data type, right? And if there is no data type, then also its amount, the amount of space that it needs, okay, will always be fixed for a particular language, right? So we will know this amount of space, and accordingly we will allocate the area in the local variables area, correct? And then local arrays we are putting at the end, okay, which you can see in the activation record structure, that it, if we want to expand them, okay, then also it is convenient. Fine. Okay, so this is how we are having all the activation record fields, okay, which are stored in the AR. In short, it is also called AR, activation record, okay, which is maintained in form of a stack and which is accessed, okay, the entries in this particular stack of activation records get accessed with the help of this static and dynamic link, okay. Now, if you want to access anything, okay, we are talking about a stack, right? So we will always have a pointer that is pointing to uh, the stack, right? Now we also need to know the variable storage offset computation, so that what is the offset of the uh, what is the offset for a particular variable which will help us to access a particular AR. Okay, so now let us try to get this. The compiler should compute the offsets at which variables and constants will be stored in the activation record. Okay, so in one activation record, we will have multiple variables, we will have lots of constants, okay, which we are going to store according to the structure that we have discussed previously, right? Then these offsets must be calculated by the compiler. These offsets will be with the respect to the pointer pointing to the beginning of the AR. Okay. So the starting of the AR, okay, that will be known to us, okay, which we will call as base. Okay. And from that, we are going to consider these offsets. The variables are usually stored in the AR in the declaration order. Now here declaration order means the order in which you are declaring the variables in your program. Okay, that is how they will get stored in our AR. Okay, but this is just a general scenario for a particular implementation. It may be different, but most of the compilers follow this particular strategy. Offsets can be easily computed while performing semantic analysis of the declaration. So, you may not have completely gone through this topic of semantic analysis, but when you do it, okay, you will realize that whenever a semantic analysis is done, okay, the size of the variables, okay, will be known at that point, okay, and then from that offsets can easily be computed. Okay, so let's take an example to understand this variable storage offset computation. Okay, now here in this example, what we have is we are having different blocks, and you can see that these blocks of code are nested within one another. They may be procedures, they may not be procedures. Okay, here in this example, we are simply considering them as blocks of code in which we are having some variables which we want to store. Now you can see that B1 is part of our procedure example, and all these B1, B2, B3, B4, and B5 are the blocks. Okay, now here B2 and B3, they will use the same storage space. Okay, and B4 and B5, okay, they can be stored in the same overlap storage, okay, because they are nested in a particular fashion inside B3. So whenever a particular whenever we are calling this procedure example, okay, at that time we may be calling it in the sequence of blocks that are being accessed, okay, they can be in this order. It can be B1, B2, okay, then it could be B1, B3, B4, or it could be B1, B3, B5, or it may be simply B1, B3, okay, not going into any of these blocks and simply termination. So in all these different cases which are possible for this particular procedure, okay, we can understand that B2 and B3 can use an overlap storage, and B4 and B5 can also use an overlap storage space. Right? Now let's try to look at how the offset can be calculated for this particular scenario. Okay. So now here we are having three variables in each of the blocks, okay, and their sizes are specified, right? So now from the size of all these variables, okay, offsets can be determined, right? So A, initially its offset is 0 because it is the first variable. Then B is stored at 10. Why at 10? Because the size of A is 10. So we simply add 0 plus 10 resulting into 10. Okay, then next variable B is again of size 10, so the offset for C will be 20. Next variable is D, okay, of block B2. Now it will be stored at offset 30 because previous value that was stored at offset 20 has got a size of 10. Similarly, you can observe in the diagram, okay, that all the offsets have been calculated. Getting this, all of you? Okay, you can just verify, right, that adding the size to the previous offset, okay, will give us the offset of the current variable, right? So, say for example, we are looking at M, right? So, if we are looking at block B5, okay, and we are looking at M over here, okay, now how its offset of 80 was calculated, okay, just let's understand this one, okay. Now, last variable stored was I, because both these blocks are stored in overlap storage, right? So we have to consider the offset of I, which is 70, okay, and it is having size 10, right? So we add 10 to it, and the offset for M will be 80. Then for next, it will be 80 plus 20, it will be 100, right? Then 100 plus 50, it will be 150, and so on if there are some further blocks. Okay, I hope all of you are getting this, right? Now, can you calculate what is the amount of storage we will need for this particular example? You have to keep in mind that we are having overlapped storage, right? So we have to just figure out what is the maximum size, okay, required for a particular block or its nesting, okay. And can you try to calculate what storage will be required for this example? Suppose we are considering all these sizes in byte, or let us just simply take 10 units, 100 units, and so on. Okay, how many units of storage will be required for this particular example? Okay, please calculate and let me know in the chat area. Okay, once you are done with it, okay, I will just discuss how the answer is correct or not. No, Mayank, it is not 300. No, it is not 310. Dipesh, 350 is correct. Okay, Hetul also 350 is correct. Okay. The answer has come up 350, but how you are supposed to calculate it? Okay. So I'm giving 1 or 2 more minutes for rest of the students. Okay, we are having 108 participants. Okay, and only 4 of you have answered. So remaining, just give it a try for 1 or 2 more minutes. Okay, see what will be the storage which we will need. Okay, then I will show you the calculation of how it is to be done. You can compare answers. Okay, so let us see what we have as answers. It seems that remaining students, okay, they are not. Maximum offset plus variable size assigned with 8. Yes. Okay, that is absolutely correct. Okay, first and foremost, what we have to do is, uh, okay, now let me just explain how the answer is 350. Okay, those of you who have got it correct, okay, whether it is done in a proper way or not, okay, that we can just find out. So now what we are supposed to do is B1 plus maximum of B2 and B3, and B3's local variables, that is G, H and I, okay, plus the maximum of block B4 and B5. So whatever is the maximum we need, okay, maximum space we need, with that we need to add, we need to take an addition. Okay, so here we can see that 30 plus maximum of 320 and 50 plus maximum of 240 and 100. Okay, so how this 240 and 100 we have for block B4 and B5? I'm sure you are able to get this one. See, sizes of all the variables are given to it, isn't it? Yes. So size of B4 is 240, sorry, and size of B5 in total is 100. So what is the maximum of these two? It is 240. So in total for B4 and B5, okay, any one of the block, if we are allocating total of 240 units, okay, then it will be sufficient. Now for B3's variables, okay, we need 50 units of memory. So 50 plus 240, we have 290. Now taking a maximum of B2 and 290. So for B2, what do we need? We need 320 units of memory. So what is the maximum of these two? It is 320, right? So 320 plus 30 gives us 350, right? So any doubt in this one? So this is how for a particular procedure the maximum storage can be known, and similarly the offsets can be calculated. Okay, just look at this example and let me know if you are having any doubt. I think it is very clear. Okay, so now let's see how it looks in our memory. Okay, this is how our overlapped variable storage, okay, for all these blocks B1, B2, B3, B4 and B5 will appear. As I said, okay, at a time what variables, okay, are alive or accessible, okay, that should be able to accommodated in the storage that we have designed. Okay, so if we are having B1, B2, okay, then it totals up to 350. Okay. If we are having B1, B3, B4, then also it is fine, right? If we are having B1, B3, B5, then also it can be accommodated in 350 units of memory that we have allocated. So we will always go for the maximum so that all the possibilities of different invocations can be satisfied. Are you all getting this, all of you? Okay, moving ahead. Now, this is one more example from your textbook. Okay, this is the example given in Tremblay and Sorensen. Okay, where our code is divided into 4 blocks. Okay, now this is how the trace of your runtime stack will look like. Okay, so first and foremost, okay, there will be one activation record for block 1, and it will store X, Y and name. X, Y and name will get stored. So there will be a data area dedicated for X variable, Y variable and name variable. Then if you look at the code, then next is our procedure, next is our block 1. Okay, so over here we are having a local variable x and an argument, okay, that is int. So the parameter int and the variable x, its data area will be allocated in our stack. Okay, so now our activation 2 will be on top of activation record 1. Then the third block, okay, that we have is having one integer, okay, passed as an argument. So we will call it parameter j, which will be in our activation record number 3. Then we have one more block inside it, okay, which is having an array f and a logical variable test1. Now this code is of Pascal programming. Okay, so we may find that the data type and the way it has been declared is slightly different, but it is just for example. But the way nesting is done, okay, it is applicable to all the different type of languages. Then once we are at activation record 4, okay, we have data area for f and test1, right? Now when all these blocks will end or when they will terminate, okay, what will be the case? Let us see. Okay, so first and foremost, the area that was allocated, data area that was allocated for F and test one will get released. Then the activation record number 3 will get released. Then activation area, that activation record area for the second block will get released. And finally, the activation record for 1 will be released. That is the whole procedure has terminated and all the memory will be released. So this is how your runtime stack will behave. And because it is a stack, okay, it is accessible only from the top of the stack. So once something is pushed in, right, then it can be removed from the stack only from its top. Okay, so this is how we can show a trace of runtime stack, okay, for this particular example. So you can do it for different blocks of code and try to understand. This is just for example, okay, so that we understand that how the runtime stack behaves. Okay, rather how the activation records are stored in the stack and how they are released, okay, or removed from the runtime stack. Fine. Now we are taking a very interesting example of how nested procedures, okay, are allocated. Now, first and foremost, let us try to understand the program. Okay, this is once again a new program that we are trying to look at. Okay, and its call sequence goes like this, right? So before we look at the call sequence, let us try to understand the program, how it is nested. So our main program is RTST. Okay, then it is containing a procedure P. So code of procedure P is nested within our main, that is RTST. Inside P, we have two procedures Q and R. Now Q and R are at the same level. Okay, they are inside P. Now from Q, we can invoke R, and from R, we can invoke Q. Then after the definition for Q and R is over, okay, we are making an invocation to procedure R from procedure P. We are making an invocation of procedure R from procedure P, and then we are making a invocation to procedure P from our main. Okay, so how the sequence of call for all these procedures will happen? Okay, it goes something like this. So from main, P will be called. Then from P, R is called. Okay, so this is as it is given in our program, right? Then when R is called, it is going to call Q because it is part of its definition, right? Now Q will call R. So this recursion will go on for some time, right? So there must there we are assuming that there is some condition which helps us terminate this. Okay, and all the recursions, if you don't want it to go into an infinite, okay, it will have some termination condition. So once it is met, okay, at that time this procedure will stop. Okay, this recursion will stop and there will be a traceback. Okay, so right now we are just looking at how this allocation of memory is going to be done for this nested procedure. These activation records are created at entry time and they are destroyed at exit time. Okay. So this must be very clear, okay, regarding the activation record and how what information it is going to contain. Now, how to access the variables declared in various procedures. First and foremost, we must know that which procedures variables can be accessed by which other procedure. Okay, because of this nesting of procedure structure which we have taken as an example. Okay, so I hope that the sequence of procedure call and the way these procedures are defined inside some other procedure is clear to everybody. Okay, is the program clear to all? Okay, then only we can go ahead with what variables can be accessed and what we are supposed to do for it. Okay, so if there was no nesting, then it would have been very simple. But we are having nesting of procedures. Okay, so this becomes very typical. Fine. Now, main program RTST cannot access variables of P, Q, and R because they are local to these procedures, right? P can access its own variables and also the variables of our main program RTST. But P cannot access variables of Q and R. Okay, because when P will be invoked, okay, there will not be any allocation for Q and R, okay, but there will be an allocation for RTST, right? And RTST is calling P, so P will have an access to variables of RTST and naturally to its own also, right? Now, though Q and R are on the same level, okay, they cannot access each other's variable, but both of them can access variables of P and RTST. So Q cannot access variables of R cannot access variables of Q, but they can access variables of P and RTS. Are you following this one? Okay. But this access also will require something which we call as link. Okay. So that we will see, right? So as of now, what we have is we only have the address of the base. Okay, we only have the starting of the activation record, and we know the offsets of the variable. Okay, so with these two information, how they can be accessed, that we know. But when is it is a case of nesting, okay, then what happens that we are trying to realize. Okay, any doubt so far? See, if the scenario is clear to you, then it will be very easy for you to understand that how different things are working. Okay, so let's just move ahead. Okay. Now, see, try to understand this scenario. From main, we are calling P, right? So when P is called, activation record of P is going to be made, right? Base pointer plus the offset, okay, will be used or it can be used to access the local variables of P. We have said that P can access variables of main, that is our RTST, right? Can this base pointer be used to access the variables of main? What do you think? Let me repeat my question and then maybe you will be able to answer it. Okay. See, whenever a procedure is called, its activation record will be made, right? So first RTST is called, right? Its activation record will be there containing all the variables which are part of RTST, right? Now, after this allocation is done, okay, RTST is calling P, right? So when P is called, its activation record will be made and it will be stored on the stack, right? Now, if I want to access the variables of P, then I always know the base pointer of the activation record for P. So plus the offset can give me the access to the local variables of P. Getting this, all of you? Okay. Now, P can also access variables of RTST. Is that correct? Yes? Okay. Now, can I use this base pointer to access the variables of main? Namish, JS allows it. You mean JavaScript is allowing this access to the main variables? Is that correct? That is what you are trying to say? Yes. Okay, so it does allow, but how to do it? Okay, that is the question. It allows it. See, that is there. From P, you can access variables of RTST, but can you use the same base pointer? See, same base pointer cannot be used, okay, because it is a different activation record altogether that we are talking about, right? So base address plus offset will give us variables which are local to that procedure. But if there is some procedure, okay, which is above it or which is enclosing our procedure, so RTST is enclosing P, so this base pointer of P cannot be used to access variables which are local to RTST. Are you getting this one? This should be clear that you cannot use the same base pointer, right? So we need something else, okay, that will help us maintain this connection between P and RTST and for further procedures also. Following this, okay. So for that, we will learn two concepts, okay, that is static link and dynamic link. Okay, so if you remember the structure of the activation record, okay, we were having these, there was one field which was storing this dynamic link and static link. Okay, so over here, first and foremost, the dynamic link chain is very simple. Okay, it is chaining all the activation records in order to maintain the stack structure, right? So from which procedure, which one was called, okay, that link is maintained by our dynamic link chain. Okay. Now to access the variables of RTST in P or in further procedures also, okay, static link field of the activation record has to be put in the register. Okay. The content of that activation of that register will now point to the beginning of the activation record for RTST. Getting this? Okay. So we will be maintaining a static link to the activation record, okay, which we want to access in further procedures. Right. Now we need to consider this value and access the variables of RTST using the offset. Okay. So if a static link is maintained for a particular procedure in another procedure, okay, then that uh, activation record can be accessed, okay, and further its variables also. Are you following this, all of you? Okay. So now for our nested procedure, this static link becomes significant. Dynamic link will already be there, okay, because it has to maintain the stack structure. So dynamic link chain is already maintained, but then we have a concept of static link, okay, which we can use. Okay. So now how this static link, okay, will be used for the procedures P, Q, and R, okay, that we will discuss in the next lecture. Okay. Uh, so this is how the static link chain is maintained. Okay. So we will take this call sequence, right? And we will trace out this nested procedure to understand that how the link is maintained and how the values for different variables which are local to a particular procedure can be accessed. Okay. So I'm going to stop at this point. We will take the entire trace all together in the next class. So if you are having any doubts, then I'm here for one more minute. Okay, you can ask them in the chat area. Okay, for any topic which you have not understood or which requires more explanation, right? And then I'm going to conclude the lecture. Okay, it seems that whatever has been covered so far is understood by all of you, so that is good. If you still have doubts regarding any topic which we have covered so far, please let me know. Okay, so I'm stopping the sharing of my screen, right? Okay, so I'm concluding the lecture, right? All of you, please have a nice day.
Good morning, all. Again, today I have another setup for the audio. Let me know whether I am audible or not. Just one feedback initially. Am I audible to you? Okay, that's good. So that's good. Okay. Uh, Submission of Lab 6 recruitment process next week and exams. You want to postpone the submission of Lab 6? Okay, so what we can do next week? Which company is coming? Which company is coming next week? Okay, we will adjust. You just see what will happen now. In the, assignment 7, I am going to give you after examination. For 6, when you have examination from 24th. So, when would you like to submit your assignment 6? According to your choice only. Advanced India is coming. Okay, fine. Okay, so when would you like to have in the next week after your exam? So, can I have the Wednesday, Thursday after your exam? That suppose your exam completes on Friday, can I keep it on Wednesday, Thursday of that week? The next week after? Okay, fine. So we will keep that. I will extend the deadline, right? I'm not sure about the date, but after your exam week, I will keep it on Wednesday. Or I'm keeping it on Wednesday so that further assignments can be submitted. But then assignment 6 and 7 deadlines will be nearby, right? So we just make sure that it will be completed. So if you have time, just keep completing it. If you don't, then definitely we will extend because your of course the recruitment process is even more important than anything else, right? Fine, so no issues. I'm keeping it on Wednesday, Thursday, right? But it will lead few assignments. The deadlines will come back to back. So just you make sure about you just be aware about the dates of deadlines. Fine, but now onwards all the assignments will come after your exam, right? Okay, no issues. Anything else if you want? Any doubts regarding to lab or anything else? Any other doubt? Okay, last time, so I'll repeat the thing that I concluded last time that was regarding to cos theta or cos omega t for Fourier transform of cos omega t because I was not satisfied with the coverage of it. So I will repeat it in case you have gone through. If you are comfortable, then you can just go through it. That okay. So I have to repeat it because I was not satisfied there, right? So what was my point? Well, my point was that if I want to find out Fourier transform of cos omega t or cos omega 0 t, Cos omega 0 means what? That it is existing at omega 0 frequency. Omega 0, if I want to represent it as frequency in hertz, then I should write it as cos omega, I mean cos 2 pi f0t or cos 2 pi mu 0t. Okay, so what I have here is, what I will have here is that if I have, let me check if I have that one already, that will be needed somewhere after some time, so it is required to be completed now. uh, yes, this is that. So what I want is, I want to find out Fourier transform of cos 2 pi f0 mu 0 at whatever the frequency of my signal is a here. Frequency of my signal, my cosine signal, if I have my cosine signal, then frequency of that signal is a. So how I will represent it as cos 2 pi f0 a mu 0, whatever you want to call it. This is a specific frequency of my cosine. This is a frequency signal, right? So I know that how to represent this cos. I can represent this cos as that I can represent this cos as definition in terms of exponential. So what it is, e raised to j theta plus e raised to minus j theta divided by 2. Here theta is 2 pi 8. So it is my theta. So this is e raised to I theta plus e raised to minus I theta divided by 2. And this is the definition. This is the definition of my Fourier transform itself. Then what will happen? So this is the Fourier transform definition, that minus infinite to plus infinite function e raised to minus j 2 pi ft, 2 pi mu t, whatever you call, right? E raised to minus j 2 pi mu t dt. That is what my definition of my Fourier transform is. So you represent it. See, what I have here is, I, instead of representing my signal as mu, I represent it as f. So I will have f minus f0. F was that mu was also in terms. So you can, if you don't want to go in detail here, you can consider as mu. It's all right. You can consider as mu t. No issues. I am just changing the variable there. Okay, so now what will happen, that this will the 1 by 2 is common from the integration, and this exponential will get multiplied with the both terms, and I'm going to get this definition. This is what I'm going to get. Now if I will observe this carefully, then what I will get is, this is Fourier transform definition of this function. What is the Fourier transform definition? Integration function into e raised to minus j 2 pi mu t or 2 pi ft. This is what the definition is. So this is actually the definition of Fourier transform of this. This is actually definition of Fourier transform of this. And if I will see what is the Fourier transform of such function, so I know that Fourier transform of such function is e raised to j 2 pi mu 0 t is delta mu minus mu 0. So in my case, it is e raised to j 2 pi at. Here it is at. So what I will have, mu minus a0. I mean mu minus a. Here instead of mu 0, I have a. So I am going to have delta mu minus a. Or I can say, if I'm not using mu, I can use variable f I'm using instead of mu. So I can write f minus a. Or if I'm using mu, whatever variable I'm using, I'm going to write mu minus a. And here, if you will observe, this is e raised to, if it is a minus case, you can consider it as minus here. That is, you can consider that it is negative frequency a. So you can write it here plus a. Mu minus minus a, that is mu plus a. So that is what I have. So if I will plot it, what I will plot, if I will plot what it is, mu is my axis, mu is my frequency axis, and minus a means what? Minus a, it is right shifted by a, and right shifted by a. It is impulse right shifted by a. This is impulse left shifted by a. So I have one impulse left shifted by a, and so this is what I'm going to get as my Fourier transform. So this is what my Fourier transform is. What it is, that two impulses located at, what you can say, plus a and minus a. Okay, so this is what I wanted to tell you. So if you want to find out for Fourier transform of cos, it will look like this. Okay, what is this DC term and that we are going to get, that is remaining, this portion is remaining. We will cover this, but I think you should understand that at frequency f, if my cosine exists at frequency f, I will have one impulse here, I will have another impulse here. What is this? That will come, that I will cover. But right now these two terms you must be clear with, so at that time we will not require to repeat it again, this and this. Okay. Same way you can check for the sign. You can, so what is your assignment? Your assignment or your practice example is for sign. You can try. You can try for the sign, and you can try for the exponential function, shifted exponential. Everything you can try. Okay. So if you want to check that, if you want to practice this Fourier transform, already I think you have gone through so many examples of finding Fourier transform in your course Maths 3. If not, then already if you will search on the internet, so many examples are available to find Fourier transform. So, so that is what was my last discussion. I hope it is clear to you now that cosine, if I have cosine at particular frequency mu 0, the Fourier transform of it is two impulses located at plus mu 0 and minus mu 0. That's it. That is what my conclusion is. Now, one more question, one more example of finding Fourier transform. Just find Fourier transform of this. Now tell me the steps one by one what it will be. What I want Fourier transform of this. So what is the what it should be? So my equation says from minus infinite to plus infinite. I should have my function from minus infinite to plus infinite. If I want to find out Fourier transform of f of t, I should write f of t here, and I should have exponential term here into f of t into e raised to what we can have minus j 2 pi mu, okay, 2 pi mu and t. And what is the variable here? Variable is dt. So I will have, this is what I am having as my Fourier transform definition. But so I will substitute f of t here. But what is f of t? From minus infinity, if I will check, my f of t is 0 till w by 2. And from w by 2 onwards, I mean plus w by 2 onwards, till infinite, it is 0. So whatever the, what if I, even if I'm integrating from minus infinite to plus infinite, it is going to get multiplied with exponential. My values of my function from minus infinite to w by minus w by 2 is 0. From w by 2 to plus infinite is 0. So this integral must reduce to minus w by 2 to plus w by 2, because other values, for other values the integral is going to be 0 anyway. Okay, so this is what the definition, and this term as it is. So integral is now that only. So from minus w by 2 to w by 2, f of t exists. But what is the value of f of t for in this range? So my f of t is actually a. My f of t is actually a. In this range, my f of t is a and exponential as it is. This exponential, I'm not repeating it, it is as it is. Okay, now what will be my next step? Can anyone tell me for the next step? This, what will happen to this a? A will come out of this integral. So it will be like a, then integral of from minus w by 2 to plus w by t, e raised to minus j, that term, e raised to minus j 2 pi mu t and the dt. Now do this integral, what will be your integral result? Give me the integral result here. Substitute the limits and give me the final answer. Quick, and give me the final answer, what it will be. Exponential, you know that up to this, I think everyone should be clear, right? It is my minus w by 2 to w by 2. It is my function a and my exponential there. Then a will come out. Then what will happen? Exponential is going to get integrated from minus w by 2 to w by 2. And what is the integration of that? Integration of that exponential is e raised to x is e raised to x only. But what will happen? That extra terms are going to get divided here, so that you can understand that negative is also came out. It is divided here. I guess you can understand this. Okay, so now w by 2 is substituted here. So observe. So this 2 will get cancelled here if the t is getting. So which variable will get the value? It will t will get the value because t is my variable. So here t is replaced with w by 2, then t is replaced with minus w by 2, and this is the solution that by 2, that division of the denominator is getting cancelled by this 2. So that is what I have here. Now further, if I simplify it, if I use this 2j, if I use this 2j here, and if I change the order of this negative terms, if I get multiplied this minus 1 inside, what will be, can I say it is going to look like A by pi mu. It will look like A by pi mu. And what will be this term? What will be the inside term? What is the definition? E raised to minus j pi mu w minus e raised to minus j pi mu w divided by 2j. What exactly it is? This 2j is coming here. 2j is coming here. What is that term? What is that term? Can anyone tell me? Anyone? Are you following the point? It will be sine. Yes, it will be a sine term because it is e raised to x minus e raised to minus x divided by 2j. So it is a sine term. It is actually sine pi mu w. It is e raised to j theta minus e raised to minus j theta divided by 2j. So theta here is pi mu w. So what it will be? It will be just pi. It will be sine pi mu w. It will be sine pi mu w. Okay. Now, if I have pi mu in the denominator, pi mu is in the denominator. The sine term here, there will be sine term, right? Okay. So if the sine term is there, pi mu is there, a is being multiplied. If I multiply and divide with the w, can I say I'm going to get this? Okay. But someone may say, okay, why are you interested in having? So what exactly I obtained here? Sine term and the same theta is in the denominator. So actually, I obtained sine x by x. It is sine x by x. It is sine x by x. Okay, and the AW is multiplied with this. You can say it is amplitude of the sine x by x. So what means my conclusion that if I am having a rectangle in my time domain, its frequency domain is going to be sine x by x, and it is defined as one function sinc x. This is defined as sinc x. It is very important function now onwards for us. It is sinc x. This is what is sinc x? It is sine x by x. Now, can you tell me how it is going to look like? What will be the look of that? So, if you will observe, it is including sine x term. What sine x is? It is having oscillations. It is having oscillations. Can you tell me when this sinc x is going to be zero? So what I've concluded till time that sinc x is a function which is sine x by x. I just what my next question is how it is looking like, how its shape is like. Okay, so I need some basic questions here. First is that it is consisting of sine x term, so it is going to have some oscillations for sure because sine x is having the oscillations. Two questions now. When this function is going to be zero? When this function is going to be zero? Sinc function is when any function goes to zero, when it will be zero, when sinc x is going to be zero, what will be no x is equal to not like zeros. I mean when it will not. Okay, so my question was wrong here, Maliha. The point is when it will touch to horizontal line, when it will have the zeros. Like sin x is having 0 k pi. At every pi, it is having value 0. That is what my question. When sinc x is going to be 0? When it will have 0 values? Yes, we can say whenever sin x is 0 or when it is k pi are the zeros of sin x. So whenever sin x is 0, it is going to sinc this function is going to be 0. So I want to plot it. I want to see how it will look like. So I'm sure that at pi because sin is 0, if my x value is pi, sin pi is 0. That's why sin pi by pi will be 0, and hence sinc function is going to be 0. So at pi it is going to be 0. At 2 pi it is going to be 0, right? Same way it is 3 pi, it is going to be 0. At k pi, it is going to be 0, right? Same way at minus pi, because sine minus pi divide by minus pi, because x is minus pi here, it is going to be 0. And at minus 2 pi, my function sinc x is also going to be 0, right? And so what I have is here is I am having x on this x-axis, and I am taking different values of x. X is k pi, where k is from minus infinite to plus infinite, just not 0. When so for all pi's, we have 0 values because sin x is going to be 0 there. What if x is equal to 0? That means k is equal to 0. X is equal to k pi, but k is 0, that is x itself is 0. What will happen? Will it be infinite? Sin x by x. Think on that. Sin x at that point also what will happen? X is equal to 0 at that time. What will be the value of sin? Yes, it will be 0 by 0. So when what is the value of 0 by 0? When x tends to 0, the value is going to be 0 by 0. Have you learned when x tends to 0? So what will be the limit of 0 by 0? Yes, it is going to be 1. L'Hopital's rule we have studied, right? So what will happen if it is 0 by 0, then it is going to, when x tends to 0, this term tends to 0 by 0, and hence it tends to be 1. That we have already studied. So I know that at x value 0, my function is going to be 1. At x is equal to 0, my function is going to be 1. If my x is 0, my function will have 0 by 0, and hence it is going to be 1. Okay. So I know now my function is going to get oscillated between, so my oscillations you can see, like it is having the higher value here, then it will come to 0, then it will go down, again it will come to 0, again it will go up, and you can see, I think you can see the oscillations here. Now one more thing, what will be the impact of this x? What will happen to amplitude, or what will happen to the values of my sinc x if x increases? If x increases, what will happen to values of sinc x? X is currently 0, having value 1. Now x increases on positive side or in negative side, that's all right. If x increases, what is the impact on this term? If denominator increases, what happens to the term? Yes, it is going to decrease. So my oscillations are going to reduce. And as Maya said initially only, that at infinite, what will happen? If x gets value infinite, what will happen? X gets value infinite. This oscillations will get decrease, and they ultimately will get to 0. So here I am having decaying oscillations with these zeros. So how the shape of this curve will look like? It will be like this. It is higher oscillation. Here it will be lower oscillation, then even lower, and actually after infinite time it is going to be 0. Same way here the oscillations are like this, then it will be somewhat value, then actually after some time they are going to be 0. I hope you can understand this is how. So oscillations are there because of sine, decaying oscillations are there because of because of x is divided, zeros are at zeros are at k pi, but k value cannot be 0. If it is 0, then value is 1. Everything is all right here, everything is fine to you. This is how the shape of sinc function looks like. Now, one more point. For the basic sinc function, one more point. When suppose this is my sinc x function. When my sinc x encounter its first 0, when my function sinc x encounters its first 0 at pi and minus pi, right? First 0 is encountered at pi. So whenever my argument, my x value is equal to pi, then my first 0 is encountered. Same way, my on the left hand side, if I want to check, whenever my argument is negative is equal to negative pi, then my first 0 is encountered. Same way, someone will tell you that find out sinc. What is the first 0 of sinc 3 omega by 7? So first of all, tell me what is my axis here. My variable is omega. Earlier I was having x. That's all right. Earlier I was having sinc x. So here, if you are not comfortable, we can have x here as well. 3x by 7. I think that is tribal thing you are comfortable with. So whatever, some variable 3 by 7 of variable, 3 by 7 of omega or 3 by 7 of x, whatever. So my axis is x or omega depending on what variable I have used here. Can you tell me what is my first 0? For which values of x I am going to get my first 0? So what to do? Argument should be equated to what? Argument here was equated to pi to get the first 0. Equate the same argument here with the pi. So what is my first 0? Yes, my first 0 is real is 3 pi by 7. So my first 0 is 3. I think you can understand 3 pi by 7 pi by 3. 7 pi by 3. Yes, it is 7 pi by 3. So what? How to obtain your first zero? So you are going to get it by equating your argument to 0. Okay, you are going to get it by equating your argument to 0. So that is this facts you should keep in your mind. The shape first, okay, and then first 0 that will be useful to us. Amplitude, if nothing is multiplied here, amplitude at 0 will be 1. Now my question is, what is the significance of this? What is the significance of this result? That what is the Fourier transform? Significance of this result is important to understand. What is the Fourier transform of this curve? So what was the curve? The curve was like this. The curve was like this in time domain. The curve was like this in time domain, right? Now, so now what was this frequency domain? Frequency domain was like this. What is the span of the sine sync wave? See, of course, they are decaying exponentials. Pardon me for my rough drawing, but I think you can understand the point. Like so what I want is my pulse is existing with some value in some duration of my time. It exists from minus w by 2 to w by 2 time. That is what the meaning is, right? Now, its Fourier transform of is this. What is the meaning of that? What is the meaning of Fourier transform? That these frequencies are suppose my Fourier transform is like this. What is the meaning of that? This sinusoidal of this frequency with this amplitude is existing in my curve. Suppose it is having this type of shape. What is the meaning of this? If Fourier transform of some curve is like this, what is the meaning of that? This frequency with this much amplitude, this frequency with this much amplitude, and this frequency with this much amplitude are having this three sinusoidals with particular amplitude and frequencies are combined to make my function. This type three amplitudes and the three frequencies are combined. They are added together to get my signal. That is what general meaning is. Now, same thing, that same understanding we have to develop here for our curve. What it says, to make our this pulse, how many sinusoidals I need? So how many frequencies I need? So I need frequencies from minus infinite to plus infinite. I need the frequencies from minus infinite to plus infinite. That means I need infinite sinusoidals to create my such pulse. To represent this pulse in terms of summation of sinusoidals, I need sinusoidal of this frequency, this frequency, this frequency, this frequency, all the frequencies with particular amplitude. Because my span of my curve is from minus infinite to plus infinite, I need a large number of sinusoidals with decaying amplitude. Of course, the higher frequencies amplitude, higher frequency sinusoidals amplitude will not be that large, right? But still, they must exist to make this curve. So how many frequencies, what is the frequency of this curve? Or how many frequencies are needed to make this curve? Uh, I'm not getting your point. What is the question, Priya? Where is K pi? How you judge to K pi? See, this is my frequency axis, na? See, I can repeat. No, see, this is okay. What is this? This is my frequency axis, right? So what is the meaning of that? Here, this is zero frequency. That means zero frequency. Okay, so this is my zero frequency curve. Then this is my one, whatever the frequency values change here. So what is the meaning here? That frequency, this frequency value and this amplitude. Then I need a sinusoidal of this frequency and this amplitude. I need sinusoidal of this frequency and this amplitude. I need sinusoidal of this frequency and this amplitude. Understood? So how many sinusoidals, how many frequencies I have? Infinite frequencies. So I need sinusoidals of this many frequencies. And what is the amplitude of particular frequency? So I can go to that particular frequency and check the amplitude. So what if I am checking for this, that means sinusoidal of this frequency will have this amplitude, and such infinite sinusoidals I am going to get combined. I am going to add them and I am going to make this this rectangle pulse. So what is the meaning? Whenever if you will represent this into Fourier domain, it will need infinite frequency to be represented. That means to create this pulse, I have any pulse can be represented as summation of sinusoidals, but how many sinusoidals I will need here is infinite. That is the meaning here. That is the significance here. And infinite sinusoidals having infinite frequencies, or so many number of frequencies are so many. Okay, Priyal, I think it's clear to you. Okay, okay. So right. So fine. Now, okay. Now what we are going. So that is my that is our second conclusion. Now third point that we have here is what is the. Let's plot this. Let's plot this. So can you tell me what is its first zero? I want to plot this sync function particularly. What is its first zero? Actually, you can read it as AW sync pi mu W. AW sync pi mu W. Sync sin x by x. So this is your x actually. So what is your first zero? So tell me what is the variable first? We should identify the variable. Then I will equate the argument equal to 0. Then I will get variable value. Here, what is the variable? Mayank, first tell me what is the variable? Variable is pi. What is the variable? Sorry, variable is mu or w. Pi cannot be, na? Variable is mu or w. What it is? The function is f mu. Function is f mu. That means variable is mu or w, Mayank? Yes, the variable is mu. Real variable is mu. Okay, so what I have to do? Think pi mu w should be equated to pi, and I should get the variable value. Variable is mu, so I should get it that my first zero is at mu is equal to 1 by w. I should get it as mu is equal to 1 by w. Second, so here this is 1 by w, this will be minus 1 by w. This will be 2 by w, this will be minus 2 by w. I hope you are getting the case. Okay. Now, what about amplitude? What will be the amplitude? Will it be 1? It is AW sync. I want to plot the entire one. What will be amplitude of the curve? AW sync. If I have A cos theta, what is the amplitude of it? It is A. So here what it is? So if I say it is AW sync, what is the amplitude here? If I say AW sync X, what is the amplitude of the curve? It is AW, right? It is AW, right? So here my amplitude is not 1, it is my amplitude is AW. Amplitude is AW and the width is 1 by W minus 1 by W, 2 by W minus 2 by W, so on. Okay, so that is what we should see here. So this is my time domain representation, this is my frequency domain representation, and the height is AW, I mean amplitude is AW, and the first zero is 1 by W, minus 1 by W, 2 by W, minus 2 by W, and so on. This is minus 2 by W. I hope you can understand it. Now suppose I take absolute of it. What is the meaning of absolute? Absolute is all negative values are converted to positive. Absolute is nothing but magnitude or whatever you can say. It is all the negative values are converted to positive. So this is how absolute value is going to look like. Absolute. So all the negative lobes are now converted to positive. That's it. Observe. All the negative lobes are converted to positive. So that is magnitude of f of mu, or all the negative values are converted to positive. So this is magnitude of f of mu in case somewhere if you will need. So this we must know. One more interesting thing, if you can observe, see this see observations we are going to implement for the image processing. So at that time we will not we'll be able to do this process again. So these observations you should learn and you should keep in your mind. What is W? W is the width of my rectangle pulse. W is the width of my rectangle pulse. How it relates to my sync pulse? How it relates to my sync pulse? It is also width, or it is also relating with the width and the height, of course. Width and the height of my sync pulse. If my width is higher, that means if I am having higher or broader, if I'm having broader rectangle pulse, that W, if I keep increasing the W, what will happen to my sync pulse? If broader my time domain, what will happen to my frequency domain? I am expanding W, I am increasing the value of W. If W is higher, what will happen to width of my sync pulse? W is higher. That means I am widening the pulse in the time domain. W increases, then 1 by W increases, then 1 by W decreases. That means it will be even smaller value somewhere here, which will be near to 0. Yes, Mike, it will decrease. It will decrease. So what will happen? My 1 by W will even become smaller, and the width of my main lobe decreases. Width of my time domain increases, then width of my frequency domain decreases. That means if I have infinite width here, or if I have very high width here, I will have narrow width of my frequency domain. What is the meaning of narrow width of my frequency domain? See, if I'm narrowing this down, if this pulse is narrowed down, how many frequencies are included? Included or indulged frequency will increase or decrease. If I say frequency domain is reducing or it is narrowing down, my frequency domain is going to get the width of my frequency domain is decreasing. So now included frequency or indulged frequencies will increase or decrease. That means the span will increase, which is currently from minus infinite to plus infinite values of mu will increase or decrease. Currently, the span of my frequency domain is from minus infinite value of mu to plus infinite value of mu. If I say my frequency domain is shrinking, what will happen to my available frequencies? Now my frequencies are not from minus infinite to plus infinite, but actually they will be somewhere the value will get narrowed down. They will, so now instead of going to plus infinite, it may come nearby. So possibly I will be able to handle them instead of having infinite value, though they may have large value, but they will be the value will be handleable. So that is our observation, that if I am widening the pulse here, my frequency domain is getting narrowed down, and hence now span which was from minus infinite to plus infinite earlier may get reduced to some value. Okay, so that is what the observations are. Very interesting observation from one example itself. Okay, so this we will use somewhere. Any doubt here? So what? So suppose now if I am widening my frequency domain, or if I am narrowing down my time domain, what will happen? If I'm narrowing down my time domain, my frequency domain is getting spreaded. And if I'm widening my time domain, my frequency domain is getting shrink. So expansion in time domain, shrink in frequency domain, shrink in time domain, expansion in time or frequency domain. This is duality property. This is duality property, that if you expand this will shrink. If you shrink this will expand. Okay, so this is duality property. We will need somewhere. Just have this observation with you. So now, what will be the amplitude? Amplitude is here. The problem it is the printing mistake. It should be AW. In your textbook itself, it is AT, but it should be AW. From where it will come? From where T will come? Right? It is AW. So printing mistake. But anyway, T can be the width or W can be whatever the width is, whatever this variable is. So AW. So you can just make that correction when you are reading. This is AW. Right? Figure itself says it is AW. Okay, so it is AW, that absolute of sync. AW is constant, so no meaning of taking its absolute value, but sync's absolute value is going to give you all positive lobes. Okay, so this is a very important example we have discussed so far. Now we are going to the next point. Okay, now next point is Fourier transform of impulse train. Now see, what we are actually planning to, we will do all the mathematical fundamentals first, then we will relate it with the image processing. Like as I told you earlier, fact that we concluded all are useful. How they are related to image processing is the remaining task. Same way, this is also very much useful for our image processing concept. So first we are completing all the mathematical concepts, and then we will start relating them with the image processing. So don't think that we have started the mathematical course, the mathematics we have started, and we have forgotten that our subject is image processing. We remember it. We are going to we are going to relate it, but it will take some time because so many mathematical fundamentals needed. They are to be refreshed. Okay, so now what I need is I want to find out Fourier transform of the impulse train. I want to find out Fourier transform of the impulse train. What is impulse train? Impulse train, you know that impulse located at S delta t is nothing but impulse located at the gap of delta t, at the gap of delta t. Okay. If you remember, okay, so now what I want first is, what is my approach here is, first I will find out Fourier series of Fourier series representation. Fourier series, if I find Fourier series of any function, it is just another representation. Fourier series does not change its meaning, right? So what is my purpose first? That I am going to find out Fourier series of my impulse train first. Then I will find out Fourier transform of that Fourier series because it is going to give me ease of using. It will give me the facility to use my previous results. So what I will do, I will just represent my impulse train as my Fourier series, and then I will find out its Fourier transform. So I want to find out Fourier series of impulse train, and this is given by, if you remember, that Cn e raised to j 2 pi n or omega nt. If you remember, this is omega nt, where t is the period of my signal. If you remember, already we have gone through that equation. This equation you should remember. Already we have gone through. This is that equation I am using. If I want to find out Fourier transform of any signal, I should go with this. I should go with this. So here in my case, my function is s of delta t. Can you tell me what is the period in my case? What is t in my case? T is what period of the signal. What is my signal? Signal is my impulse train, which is separated at the delta t. Can you tell me what is the period of my impulse train? What is the period of the impulse train? Are you following the point? Should I repeat this? Should I repeat this? If not, then you need to answer what is the period. Yes, period is delta t. Yes, period is delta. What is period? Period is that when my function repeats itself. So if you see that this is value 0, this is value delta t, this is value delta t, this is my value minus delta t. I hope you will understand this is minus delta t. Then if I will observe this region, minus delta t by 2 to plus delta t by 2, then my plus delta t by 2 to 3 delta t by 2, that function repeats itself. If you will observe this much region only, function repeats itself. The function repeats itself. See, function repeats itself in the delta t region. So my period of here, the period of my function is delta t. So what will happen here? My equation should be reduced to c n e raised to j 2 pi delta t n t. Now here, so what is my Cn? Cn is 1 by delta t, because my period is delta t. So 1 by delta t minus delta t by 2 to delta t by 2 f of t e raised to minus j 2 pi n t by delta t dt. Okay, wherever t is, it should be replaced with delta t. So this is delta t, this is delta t, and this is delta t. Okay. Now, if you will observe from minus delta t by 2 to plus delta t by 2, what is my function? From minus delta t by 2 to plus delta t by 2, my function is nothing but impulse. Observe. Just observe this one portion of my impulse train. Minus delta t by 2 to plus delta t by 2. It is 0, 0, 0, 0, sudden increase, and all again 0, 0, 0, 0. So what it is impulse located at 0. What is the equation of it? Equation of it is nothing but delta t. Impulse located at 0 has equation delta t. So from minus delta t by 2 to delta t by 2, my s delta t is nothing but delta t. So many deltas are there. I hope you can understand. Delta t function, S delta t function is delta t if my period is taken from minus delta t by 2 to plus delta t by 2. If I am just looking this function in this region, then it will behave as delta t, this delta t. Following the case, now you simplify. What is the simplification? What is the whenever you have the impulse multiplied with function, what is the result of that? And integration, what is the result of that? The function located at where delta exists. This delta exists at t is equal to 0 value. So what is the value? What I'm going to get is this is impulse multiplied with function and integrated. So result is the function where impulse exists. This impulse exists at t is equal to 0. If I substitute t value 0 here, I am going to get e raised to 0, and that is 1. So what is my result? My Cn is 1 by delta t. Yes, Cn is 1 by delta t. True, real. It is 1 by delta t. So that is what my Cn, I obtained the Cn. So that Cn value, okay, so Cn is 1 by delta t. I think everyone should be clear there. And that Cn value I should substitute, that Cn value should be substituted here. So what is my Fourier series? My Fourier series is summation of 1 by delta t and this exponential. Okay, where here also it will be delta t. So Cn is nothing but 1 by delta t. So so Cn is 1 by delta t. That means Cn, the coefficient is not dependent on the value of n. So it is not dependent on value of n. So it can come out because 1 by delta t is a constant. It will come out, and your equation of your Fourier series is going to look like equation of your Fourier series is going to look like Cn is 1 by delta t, and equation of your Fourier series is going to look like this. Right? Now, so if you will see, my impulse is, if I want to represent my impulse, so another way to represent my impulse is nothing but summation of exponentials. Impulse is also represented summation of exponentials. Okay, so now let us find out what I wanted. Actually, I wanted to find out Fourier transform of this. That was my original goal. But I know these two definitions are equivalent, so I want to find out actually Fourier transform of this. I wanted to find out Fourier transform of this. Why we need Fourier transform of this? That is the remaining question. We will see what is the use of it. But right now, if I want to find out Fourier transform of this, you should be comfortable with the method. The requirement, the reason is a separate issue to discuss. Okay, so you should not be confused with why we are doing so, with what we are doing, here, right? You should be clear with what we are doing now. Why we are doing is a separate question to solve. So I hope you are clear with it. If not, then please ask me the doubts. My aim is to find out Fourier transform of this. Fourier transform of this is nothing but Fourier transform of this representation, because both the representations are equivalent. So now if I want to, you know that, so if I want to find out Fourier transform of this, what I will have definition of that how to find out Fourier transform of any function. How to find out Fourier transform of any function. So we have, okay, so how to find out Fourier transform of any function. So I know that I will have integration, which is from minus infinite to plus infinite. Then I will have function, then I will have exponential minus j 2 pi mu t, j 2 pi mu t, right? And then dt. This is how I will find out Fourier transform of any function. But I know that 1 by delta t is not varying with respect to this t, and hence it can come out of the integral. So it will come out of the integral, so integral will come here. You can ignore this, and integral will come here. So from minus infinite to plus infinite. Now you know that this this you can change the order of integration and summation. That also you know. So what to do next? That even this integral will come inside this as well. It will come inside. You know that integrals can be separated out into summations. So you can do like this as well. Any doubt up to this? Any doubt up to this? What we are doing is clear to you now? Okay. Now, so now if you will observe this carefully, what we are having is it is nothing but Fourier transform of, it is nothing but the definition of Fourier transform of this exponential. So what is the Fourier transform of the exponential? So if it is e raised to j mu pi, that you know, if it is e raised to j 2 pi mu 0 t, then Fourier transform is delta mu minus mu 0. In my case, Fourier transform is of this exponential function, because this is the definition, this exponential is of definition. It is needed to make it a definition. But if I will see this, then I have Fourier transform of e raised to j 2 pi. Instead, what is the value of mu 0 in my case? Equate this to. Tell me what is the value of mu 0 in my case? What is the value of mu 0? Okay, what is the Fourier transform? Just forget about this. Tell me what is the Fourier transform of this? I know this. This is a fact known to me. I am going to use this. Yes, in my case, what will be Fourier transform of this? So what I will do, I know that I want to find out Fourier transform of this function. I am going to equate it with this. So I will come to know that mu 0 is equal to n by delta t. It will be n by delta t. Yes, in my case, mu 0 will be n by delta t. True. So what will be my function? My result will be, here my result will be delta mu minus n by delta t. Okay. Summation is as it is. Summation is with respect to n, and 1 by delta t is also there. Other terms are as it is. This 1 by delta t, this summation, and this just resulted into this. This just resulted into this. Observe. Okay, so this is Fourier transform of my this is my Fourier transform of my impulse train. This is again one more fact that you should keep in your mind. We will use it. Next is very interesting concept of convolution. Convolution, it is not a new term for you, but how it impacts in frequency domain that we need to learn. You know that actually filtering is nothing but convolution. Filtering is heart of image processing. So convolution is heart of our processing. Can we say like that? So it is possible that I am filtering in my spatial domain. I am filtering with my original image in my regular form. If I am filtering, what will be the impact of that filtering in my frequency domain that I need to learn? And that's why this topic is highly important for understanding of this entire chapter, or we can say many of the concept of the subject. So now, first of all, we have to define the definition of the convolution. It is not like just discrete signals can be convolved. In our case, if you remember that 0, 0, all so many zeros were there, 1 was there, and all other zeros were there. Then I had a window which was having 1, 2, 3, 2, 8, such values were there, if you remember. Then we flipped the window, then we scanned this entirely. But the convolution concept is not limited to image processing. Convolution concept is for any signal. If I am having this one signal, and if I am having this another signal, I can convolve these two signals. Convolution is very wide topic. Here what I had one function which I can see as a discrete signal, having 0, 0, 0, sudden one value, then 0, 0, 0, and this was having 1, 2, 3, 2, 8, such signal. This was also signal, na? This was discrete signal, this was discrete signal, but convolution can be applied to continuous signals as well. So now because we know it is a very important topic for an entire subject, so we should look at it a broader view of it. Okay, so what do we have here is convolution. We will see the broader definition of the convolution. What convolution involves? It involves few steps. What it is? First of all, what we did here, if you remember this topic, I hope you remember what I am recalling too. What was the first step that we did in the convolution? If you remember this example which I am discussing to, which I am referring to, what was the first step? Suppose I give you this W, and suppose I give you this f, what we were doing as first step? What is the difference between correlation and convolution? What is the difference between correlation and convolution? See, if you will not be able to relate it to previous case, you will not be able to relate it with all the concepts. So if you are getting it, so please kindly reply so that I can come to know that up to this is clear. Otherwise, I can revise. If not clear, then you have to tell me that it is not clear to me. So please revise. I am ready to revise, but this concept must be clear to you. Reverse the window, or I should say flip the window. That is true, Jamie. So first of all, I should flip. So first operation that I must have is flipping. So I was flipping it. Then what was my next step? What I was doing after flipping, what I was doing? What was the next step? What was the next step? So I flipped this. Then what I did? Whatever the flip version is, then what we were doing it? We were keeping the window here. Then we were keeping the window here. Then we were keeping the window here, if you remember. Yes or no? So we were scanning our entire function f. Can I say we were scanning the function f? So scanning was done from what to what? Can I say ideally it should be done from minus infinite? The scanning you should keep your w here and then you should multiply with this. But you know that multiplication is going to be 0. That's why you started with the first overlapping point. Wherever overlapping will not be there, multiplication is going to be 0. That's why you started with this. I think Ashutosh asked that question. And I show you that diagram also, that from minus infinite to plus infinite, the question, I mean that scanning should be done, if you remember. So what I was doing is scanning from, so what was my another operation? The operation was from scanning from minus infinite to plus infinite. So I was keeping my window there, and then I was scanning my entire function, and I was scanning it till the overlapping was, so I can avoid the total overlapping, right? So okay, so I was scaling from minus infinite to plus infinite. That is my second observation. What was third observation? What we were doing then? Suppose I kept it on the first overlapping point. Then what I was doing? What was my next operation? After clipping on the first overlapping point, ideally I should go from minus infinite to plus infinite. So I started with the first location, and then what was my next point? Anyone can recall? What we were doing then? If I keep it here, then yes, we have to multiply and add. We have to multiply and add. So I have one. So first of all, I was doing then multiplication of what? Function and window. Multiplication of function and window, and then addition. Why addition? Because it was a discrete signal. But what if it is? What if it is a continuous signal? It should be integration. So I should write right here integration. So four operations actually we have in convolution, and highly important steps here are, steps of the convolutions are flip, then shift. This is shifting from minus infinite to plus infinite. Flip, shift, multiply, integrate. Right? Flip, shift, multiply, integrate. Four steps are highly important for convolution. Now let us see the definition. Here instead of my w variable, I am using h variable. H is my window, function is my function itself, and this is the symbol of my convolution. This is the symbol of the convolution. So what are the steps? So first of all, you have to flip this. So now if I want to flip, okay, if you remember that w of st was my original window, then flipped window was what? Minus w, sorry, minus s minus t. If you remember, if you remember if you remember the flipped window, if you remember, the w1 was the flipped window, and how w1 was relating with w, that it was nothing but minus s minus t. So after flipping, whatever my variable was is now becoming negative. That was our observation at that time. So now if I want to flip this, whatever variable I have, that should be whatever variable I have, that should be negative. So here, what is the variable in this integral? What is the variable? Variable is not t. My variable is tau. So what I should have? I should have f tau into h tau. I mean, f tau and h tau are two my functions because my variable is tau here. But if I want to flip, I should not write as h tau. I should write it as h minus tau. So this is my first operation of h minus tau. That is my h tau is flipped. I can write it as h t, h tau, h mu, whatever. My function, my variable can be anything, right? My variable can be anything. So I'm writing it. This is, can I say this is my flipped version? Then I have to shift. You know that if my function is located here, and if I want to shift it somewhere, if I want to shift it somewhere here, then I am adding some constant, subtracting or adding some constant. So if I am writing plus t here, if I am writing plus t here, can I say it is going to shift it? This is what my shifting, this indicates some constant if is added here, some value is added here, then it will indicate the shifting. It will indicate the shifting. Whether it is the constant, the t value can be positive, t value can be negative. That's all right. T can take any value, positive or negative. So can I say it will indicate left and right shift? So this is what, so t plus t minus tau is, it is what, flipped and shifted function. So flip and shift is over. Flip and shift is over. Now if my t value is 7, it is shifted here. T value is 2, then it is shifted here. T value is 5, it is shifted here. If it is infinite, it is shifted up to infinite. So what is the meaning of that? My t can take value from minus infinite to plus infinite. Then my h of tau, which is flipped version, h of minus tau, is shifted from minus infinite to plus infinite. That is what the meaning is. So these two operations are over. Then there is a multiplication with the function. So multiplication is done. Multiplication with my function, my variable is now changed here. I can use any dummy variable for the integral. I am using it for tau. So it is f tau. And then multiplication and addition, but I know it is a continuous domain, so I should have the integral here. So this convolution definition includes what? Four operations. First flipping, then shifting, then multiplication, and then integration. Okay. Now, my t. What is this t? See, if you remember, I was shifting. This shifting was not done from my minus infinite to plus infinite. Why? Because there was not existence of my function f and w. Because if they are not existing, there is no meaning of multiplying them and adding them. So that's why this shift must be limited by the existence of f and w, and that's why it is taken as t. T is nothing but the variable of my function here, or what we can say, it indicates that I am checking the value of f at location t, and that t, if I am checking for location 1, then it will be convolution of f1 with h1 will be this, with located at 1, shifted by 1. That is what the meaning is. So the t relates here. So the t is limited by the existence of f and h. Or if, in other words, if I want to say that if I want to find the convolution at 1, then f of 1 convolves with h of 1, then I should take the shifted version of h by 1. So whatever my value I want to find, that t value I should take here. This is just observation we have. So this is all about convolution. Now how it is useful for our further discussion, that we will take in next lecture. So for now you can leave, but I hope you are clear with the convolution. 4 operations: flip, shift, multiply, integrate. Any doubt so far? Now what are the further discussions for how it will be useful? What are the results that we will take in the next lecture?